Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about, science and math. And today we're doing stoichiometry part 2 in chemistry class.
Welcome back, welcome back.
Welcome back. See, I'm thinking I need merch. Welcome back, welcome back.
Please.
I've got about almost 500 subscribers. Like over 22,000 views, so I'm a math influencer and science. Okay.
You better get your copper plate button.
I don't know. I just know I want 1,000 so that we can go live and I don't have to record it and then upload it. That's the pain. I want to get back to what I used to have on Facebook, but what was bad with Facebook is they would delete it after a little while. For YouTube, it's forever. I don't have to worry about them taking them down. All right, shh. Y'all listen. Okay, so we have been learning how to do these problems. If you were not here on Monday when we learned how to do these, you need to go watch the video. There were people who were here that were not here Monday who had not watched the video, and they were kind of panicking. So this test will be just math, yay. It will be probably 11 math problems. So you know, you miss one, you've almost lost a letter grade. So you gotta practice them and be really good. It's one level of skill for you to watch me do it and to kind of understand it. Is a whole different ball game for you to do it by yourself on a test. So you've got to practice your problems. And also, hint, hint, there will be pop tests on this one. Right now, I'm planning on the real test being on Monday, pop quiz. Monday will probably be the test, the real test. You've got all these days to learn just 11 little problems. They're all variations of one problem.
Bro, y'all is that hard.
All right. Okay, so let's talk about it. The smart board is messed up because they got me a new cable. So at least it's up here, but I'm going to write it on the regular board too. But we'll look at this part where it says, that's the wrong problem. I'm gonna have to, it's letting me scroll. It wasn't doing that before. All right. So our question says, how many molecules of hydrogen are produced by 6 grams? No, that's right. Yeah. Of 6 grams of water. Okay, so to do it, you need Avogadro's number. Now, in the other class, I actually had a warm-up on the board, but because of the smart board not working, I keep having to use the real board, and I erased it. But the warm-up question was, what is Avogadro's number?
6.24.
6.022 times 10 to the 23rd. What is it equal to in moles? 1. What's it equal to if it's a gas? How many liters is it equal to? 22.4. So that's your warm-up question. Titus, I have it listed that you're leaving at 3.
Me?
Yes, aren't you on the esports team? You're supposed to leave at 3, it says.
For what?
For a match or something. I'll call up the email. You can see it after we do the next.
Hey, I'll take it. I'm not complaining.
Okay. So the blank is that you need Avogadro's number, and that's what it is. Okay. So step 1, whenever you're doing one of these problems, is what? Write the equation, then balance it. So here's our equation. 2 hydrogens, good so far. 1 oxygen, 2 oxygens, what do I need here?
2.
So now what do I need here? 2. All right, so for those of you watching on the video, all we did was balance the equation with those 2's. Okay, so now what do we write? What we know. And so what we're given, our number we're given is 6 grams. What should it go under? The water. So over here on our next line we write 6 grams of water. What is our unknown? Hydrogen. So this is hydrogen gas. So we put question mark. And this time, instead of wanting grams, it wants molecules. Don't scroll. That's it. Okay. So you write the word molecules. You need to be really organized with these problems, and you have to write what you know and what you don't know. Don't just start doing it. Take the time to be organized. Okay, what goes on the next line? Where are we going to get them?
M&M's.
M&M's. Why do we know that we need M&M's? Graham crackers. We have delicious graham crackers. See the 6 grams? So we have to use our M&M's off the periodic table, our molar mass, and put down the next line. So for water, we go over here and we write that we have 2 H's, we have 1 O, H's weigh 1, oxygens weigh 16. 2 times 1 is 2, 1 times 16 is 16. You add them up, it's 18. You're going to put a little box so it's out of your way. So you're going to end up memorizing that water is 18 grams per mole. So that's right here, 18 grams per mole. Now, do I need
No,
the molar mass of hydrogen gas? Why not?
because it's not M&M's.
There are no delicious graham crackers, so we do not need M&Ms. Okay, no grams, we don't need M&Ms. What do we need instead to get molecules to moles? Yes.
Avogadro.
Avogadro, 6.02 times 10 to the 23rd molecules per mole.
Wait, so we only use Avogadro's number when we're trying to find molecules?
Or particles or atoms.
Okay.
You know, those words, particles, atoms, molecules is where you'll use it. So there it is, 6.02 times 10 to the 23rd molecules per mole. Now what goes on the next row? The mole ratio, that's Buddy the Elf going through the revolving door. I'll try to get the video up here as soon as they fix my TV so you can see it. So what is the mole ratio?
2.
Where did that come from?
2 and 2.
It came from the coefficients from the balanced equation. So notice, for molar mass, I do not do anything with that 2. Molar mass is just the mass of the atoms in the compound. Do not get confused and put the coefficient in twice. The coefficient only goes there. All right? So now, what do we draw? Are you? See, I gave you a big smile
Start from what you know.
to remind you. Start with what you know and go to what you don't know. So put a little dot, draw your U around, and now we're ready to
Train track.
We're going to do our train track. So what do we write first on our train track?
6 grams.
What we know, 6 grams. 6 grams, I'm going to put big W for water. What goes a catty corner to the denominator?
Water.
Grams of water. It helps if you make a sound effect. That will remind you to push it down there. So that is this gram. What number goes with it?
18.
18. What's on the other side of the fraction bar? Moles. What number goes with that mole? 1. Understood 1. Because it's this mole. Now we go on around here. What goes in the bottom of the fraction bar? Moles of water. What number goes with this mole of water? 2. What's on the other side of the fraction bar? 2 moles of hydrogen. Does everybody understand that? If you mess up the problem, you're going to mess it up right there. It'll be one that they're not both 2's and you'll flip it. I've graded this too many decades to be surprised by where the kids mess up, and that's it. Or else they have absolutely no idea and just write down random things that have nothing to do with anything. All right, so now what goes across the diagonal? Ka-chung! Moles of hydrogen. See, don't the sound effects help? Okay, and what number goes with this mole?
1.
Understood 1. What's the other side of the fraction bar? 6.02 times 10 to the 23rd molecules. So now we see if we did it right. Grams of water cancel out, moles of water cancel out, moles of hydrogen cancel out. We're left with molecules of hydrogen, and that's what we were looking for, molecules of hydrogen. So now, everything on top you multiply, everything on bottom you divide.
Would you put the Avogadro's number in parentheses when you do it?
You don't have to. If you use your EE button on your calculator, you don't have to do that.
Wait.
And the answer is 2 times 10 to the 23rd molecules of hydrogen gas. So, try it on your calculator. I would do 6.
2 to the 10.
Let me tell you how I put it in my calculator. 6 times 2 times 6.02, second E, so second comma, which gives you the E or EE, 23, enter, divided by 18, enter, divided by 2, enter.
Wait, what?
I'll say it again. This is how I put it in my calculator. 6 times 2 times 6.02, second comma, or however you get to the E or EE button on your calculator. If you got a TI 84 or 83, it's second comma. 23, enter, divided by 18, enter, divided by 2, enter.
So it would be 6.02E.
23.
Oh, yeah, okay.
E means times 10.
23 and then
Enter, then divide by 18, enter, divide by 2, enter. There is a way to do it without hitting enter after every denominator thing using parentheses, but I think this is a little easier. The way, I'll tell you how to do it in case anybody really wants to. You would do 6 times 2 times 6.02, second E 23, enter, divided by beginning parentheses 18 times 2 in parentheses, enter. But I think the parentheses make it harder. Now, if you don't have, parentheses, if you're getting the wrong answer, you might want to try the parentheses way. I always tell kids they never regret too many parentheses, but they often do too few. If you will hold that really straight going in there, try to be very perpendicular, then it does pretty good. And sometimes you have to pull it out and see how it's doing and turn it. The electric pencil sharpener is broken. We're having to do it old school. And it's a broken old one. It doesn't even have the outside part that holds the pencil straight. The outside part that is what holds it in there straight. All right, any questions about this one? How do we feel? Are we getting the right answer on our calculators? Remember to bring your calculator every day because there's going to be a pop quiz. It's not really very poppy because I'm telling you there's going to be pop quizzes.
So anytime you're trying to find molecules of something, it'll always be Avogadro.
Yes, molecules or particles or atoms. Those are the words where you use Avogadro's number. What did you say? Talk louder. Okay. All right, can I erase it now? May I erase? Are we good? All right. I don't remember teaching. Maybe I did. Yeah, I did. Yeah. Okay. All right, let's do the next one. This is the one I remember doing. Okay. So with this one, our equation is carbon monoxide plus hydrogen gas, and I was so nice, I balanced it for you, yields methanol. Okay, now let's read the problem together. Okay, so we give our little check because we balanced it. Check. All right, so let's read the problem. If you had 152.5 grams of carbon monoxide and 24.5 grams of hydrogen making methanol, what is your limiting reactant? Okay, so this sounds a little confusing, but if you think about brownies, it'll make sense. Let me scroll up so you can just look. Well, you got them. Just do a little bit here. All right, so don't look at anything else, just look at the brownies and think about this. Okay, say I'm going to an event and I'm going to bring 4 boxes of brownies to my event, and I go to the grocery store and I buy my favorite brownies, Ghirardelli double chocolate, the one that's got the chocolate chips, by far the best. Okay, so I want to take a lot, I want to be generous, I buy 4 boxes of brownies, I go home and I have paid my water bill. So if I turn on the sink, there's plenty of water. I look in the pantry, there's a giant thing of oil, good on oil. But I open the refrigerator and there's only 2 eggs. The mix calls for an egg per box. How many boxes can I make? 2. So even though I have plenty of brownie mix, plenty of water, plenty of oil, I can only make 2 because eggs were my limiting reactant or limiting reagent. So you will have these problems. You're going to have it on this test and you're going to have it in college. And how it works is, instead of having one given, you're given two. You do the problem twice. You just do it twice. Do it with one given and then get what you know, and then do it with the other one of what you know. Then you look at your two answers. Whichever one is less is what really happens. I had 4 boxes of brownies, but I couldn't make 4 boxes. I only had 2 eggs. 2 eggs is what limited it. It's what would have made less. Does that kind of make sense to you? We're just going to do the problem we've been doing, but we're going to do it twice. We're going to look at our 2 answers. We're going to remember 3rd grade, greater than, less than, alligator or baby bird or Pac-Man, whichever one you prefer. Whichever one is less is what really happens. And that whatever chemical that when you do that one that you use for your known, that's your limiting reactant. Yes, Lana?
Since there's 2 things that you know, how do you know where to start your what?
Where to start your what?
Your what?
I'm going to do it twice. So I'll show you. All right. So I'm going to start with, first I'm going to write underneath them what I know. For carbon monoxide, I know 152.5 grams. Okay. For hydrogen, I know 24.5 grams. And what I don't know, let's see if we can find another color. Do I have any other good colors, or are they're all orange? I don't want to do black. Hold on, we are in need of another color to make this most interesting. How about green? I think green will work. Okay. So then my question, what I don't know, is grams of methanol. Okay. Now, do I need M&Ms? Yes, because I have delicious graham crackers. Where do I get M&Ms? The periodic table. So I'm going to start, the first time I do this, I'm going to use carbon monoxide. So over here I've got 1 carbon and I've got 1 oxygen. Carbon is 12 and oxygen is 16. Shh. If you have a question, ask me. So the molar mass of carbon monoxide is 28 grams per mole. Everybody good with that? Okay, what's the molar mass of hydrogen?
618.
Hydrogen, that's water. There's, how many do I have?
2.
So what is it? 2. Everybody understand how they did that? It's 2 grams per mole because there are 2 hydrogens, and you've memorized by now that hydrogens weigh 1. Okay, now let's do the methanol. Get my green here. Okay, so I'll list them. Carbon, I've got 1. Hydrogen, I've got 4. Oxygen, I've got 1. Times 12 times 1 times 16. 12, 4, 16. That's 16 to 16, 32. So this one is 32 grams per mole. Put this in a little box so it's out of your way. All right, now I'm going to write my mole ratio. Where do I get the mole ratio from? The coefficients. So I'm going to color code it. It's 1 to 2 to 2 to 1. All right. Everybody good so far? So those of you in YouTube land. So we wrote down our knowns and unknowns for each one. We've got the molar mass of each one so far. I don't know why I did that. And we got a ratio, 1 to 2 to 1. So now I do it twice. And I'm going to start with carbon monoxide just because it's on the left. It seems like you should do it first. And so what I do is I write down that I'm going to start with carbon monoxide and I draw my U. And my U starts here and it goes to there. So my U starts here and it goes to there. Good so far? Okay, so I'm going to start with writing what I, and what is it for carbon monoxide? 152.5 grams carbon monoxide. What goes in the denominator? What?
Carbon.
We'll write grams of carbon monoxide first, and what number goes with grams? 28, and what's on the other side of the fraction bar?
Moles.
What number goes with moles?
1.
Okay. What goes catty corner on the fraction bar? Always this. Push it down there. Moles of carbon monoxide. What number goes with moles of carbon monoxide? 1. Now, we are not doing the hydrogen, so I'm just going to cover that up. What goes on the other side of the fraction bar?
1 mole of methanol.
1 mole, and we'll call it just big M for methanol. Now, what goes across the fraction bar from 1 mole of methanol? 1 mole of methanol, and that's this mole right here. What goes on the other side of the fraction bar?
32 grams.
32 grams of methanol.
So you do one problem for each known factor?
Yes.
Okay.
And then you just do it twice. We see if it marks out. Grams of methanol marks out. Moles of methanol mark out. Of carbon monoxide. Moles of methanol mark out. We're left with grams of methanol. So now every number on top you multiply. Every number on bottom you divide. Put it in your calculator and see what you got.
174.
Okay. So did everybody get 174 grams?
Yeah.
Okay. So now we're going to do it again. This time I'm going to use my orange pen. I'm going to scroll this up so people on Facebook, not Facebook, whatever this thing is, YouTube,
Do you
can
use
see
Facebook,
it.
Ms. Blackburn?
What?
Do you use Facebook?
I used to use it for teaching. I would record all the lessons I did, and I would do Facebook Live, so the kids who were out had to watch it at that time, but then it recorded it, but then they go away after a few months. But I used it for about 5 years. And then I made the big switch when COVID happened to YouTube.
And you already have 500 subscribers?
Yes. No, yeah.
You're famous.
Like, 500 people love you.
Yeah, I do. Like, people will meet me and be very excited that I've been able to help their children with math. It's mostly moms. I've had moms in tears on my front porch because they're been looking for help with their child and then got it and feeling happy about that. So, so your mothers get very invested in your math and science understanding. That's all I can say. All right, so we're going to do it one more time. This time I'm going to write H2 out to the side. And now we start with what we know, and this time it's 24.5 grams. And this one is H2. So what goes catty cornering down?
Grams of H2.
Grams of H2. What number goes with grams of H2? 2. What goes on the other side of the fraction bar? 1 mole of H2. What goes catty cornering down?
Mole of H2.
And what number goes with that mole of H2? 2. It's this 2 right here. And now what goes on the other side of the fraction bar?
Methanol.
1 mole of methanol. What goes catty corner?
1 mole methanol.
1 mole of methanol, which is this mole right here. And then on the other side of the fraction bar? 32 grams of methanol. Put it in your calculator and see what it is. While y'all do that, I'll put it here. So here's our grams of this. Oops.
196.
196.
Easy.
Okay, so now you ask yourself, 174 blank, 196, back in 3rd grade, which is less? Which one's more? Which one does Pac-Man want to eat? Pac-Man wants to eat the 196, so 174 is less, so this is what really happens. This one is less, 174 is less than 196, so that's what really happens.
So in like a testing situation, how would we go about like saying that was our final answer?
It'll be a question like this. Then the next question will say which one limits the reaction, And the answer is carbon monoxide because it's less. So how much does the reaction really produce? Theoretically, 174 grams.
Wait, so Pac-Man eats the one that's less?
No, Pac-Man eats the one that was more, but this says 174 is less than 196. Remember how to read these from 3rd grade?
No. I never understood that.
The mouth always wants to go to the one that's more. But if the one that's less is on the left side, you read it 174 is less than 196. If 196 was written on the left and Pac-Man was facing the other way, then you would read it 196 is greater than 174.
Oh.
See? All right, how do we feel about that?
Pretty clean.
And this problem is worth a lot on the test because you have to do it twice. Then you have to understand it and tell me which one limits. And you have to tell me how much you really get. So it's worth like 4 problems. So this is one you want to make sure you can do. All right. So moving right along.
Last page?
Last page.
Oh, last page, oh, yeah. Well, yes.
All of these problems are similar. It's really just like one problem with a bunch of different aspects, except the last bit I'm about to teach you.
This is gonna be on the
Yeah, this isn't hard. All right. And this is the next part of the problem. Remember I told you this problem is multi-step? Okay, and this is the next part of really that same problem. The problem says, if you did the reaction, but only got 150 grams, what was your percent yield? So, when you do the math, it's how much you're supposed to get if everything just goes perfect. But we know in reality, when you take a test tube and you pour it out into another test tube, do you get every molecule that's in there out? No, there's always some droplets. We don't have a tiny little spatula to get all the goodness out, like Martha Stewart used to say. So you got to, so some of it gets lost there. Also, you might be a little messy in lab and spill a little. I know you have, because these hot plates we have here have got a few little spills on it. Y'all have not been perfect with your keeping all of your stuff together. Now, sometimes you get a little less. Sometimes you get more. Now, where could that come from if you get more than what you're supposed to when matter cannot be created or destroyed? From what? Where? Maybe you added too much or something. Another thing is it could have some trash in it. Maybe your beaker wasn't completely clean, or maybe some debris fell into it. But that's not where it usually comes from. Where it usually comes from is you're doing a reaction in water, and then you have to dry it out and weigh your product. But you don't dry it out good enough. And so what you're really weighing, instead of weighing your product, you end up weighing the water. So that's usually where it comes from if it's more than 100%. So this is how you do the problem. And I'm actually going to change this a little bit. I'm going to erase this and put it on the board because it's a little confusing. Little confusing. But it's an easy problem. This is probably the easiest problem on the test. Composition is not here. Must be somewhere else. All right. So this is what it is. The formula is your actual divided by your theoretical times 100. And your answer will be a percent. So your actual is what you really got in lab divided by what you were supposed to get, your theoretical times 100. So what we actually got, according to this problem, was 150 grams. We were supposed to get the lesser number, 174. We multiply it times 100, and that'll tell us our percent yield. And do it on your calculator. Make sure you get 86. Notice you do not touch that percent button on your calculator. No, don't touch it. Any questions about that? Yes, sir?
Why the actual 150?
Because they told us. If you did the reaction but only got 150 grams, what was your percent yield?
So how do you know it's actual?
Because you did it. You did the lab. You did it, and this is what you got.
So 174 is what it's supposed to be?
Yeah. But we lost some. We lost 14 grams somewhere. So, and that's how it is in real life. My son Nathan, he works at Tech and is in school there. And he did an experiment that he was supposed, it's a new experiment. No one's ever done it before. It's new research he's doing. And he got 74 was his percent yield. And he was really happy. That was higher than he thought he was going to get. So he and the professor working over him in the lab were very happy with the 74% yield for this brand new thing that they're creating. So that's kind of fun. All right. So the last little thing we're going to talk about are things that affect reactions. So if I wanted a reaction to go better, what are some things I could do to help it out? I could heat it up, right? A lot of times things react better if you heat them up. What else could I do? I could put it under pressure and I could add more stuff. So we can increase the temperature, or we can increase the concentration or increase the pressure. The chemist who discovered all this, I say his name, Le Chatelier. I'm sure it's wrong because it's French and they don't pronounce all the letters. So someone in my other class who's in honors French, whatever, he tried to pronounce it using the rules of French and it sounded a little like a bad word. So I'm just sticking with Le Chatelier, saying it all wrong in Southern and all the vowels and all the consonants. So yeah, it was a little bit too close to a bad word. We're just sticking with this name.
Is that an egg?
It's temperature, concentration, pressure, and his name is Lecha with a little hat on top.
Oh, an accent.
Telier. See, it sounds kind of bad, doesn't it? We're not going to say that. Now, why would this help a reaction happen? And it's his idea. It's called collision theory. Let me roll it up. His idea is that for chemicals to react, they have to come in contact. So one way that you can make them react is heat them up. That means they're zipping around faster. They're zipping around with more energy. They're going to collide better, and they're going to react better. If you add more, they're more likely to run into each other. They're more likely to have those collisions and react. And if you put them under pressure, they're going to be closer together if it's a gas, and they're going to be more likely to react, more likely to collide and react. Does that make sense to you? Imagine the little molecules, you got to get them together so they can react. Now this, from what first period said, y'all learned in 8th grade, activation energy. Do you remember that?
Yep, Miss Corley.
Good teacher. All right. So here I have a match, and I'm holding it, this chemical and that chemical. Why am I not afraid that it's about to suddenly go off?
Because you haven't moved yet.
Right. So if I move, that's going to cause friction. And when you have friction, it causes heat, right? Rub your hands together just a second and you'll start feeling it. That little bit of heat, that little bit of energy, gives the energy it needs to overcome this little hill that is required. But once I overcome that, it can keep going on its own. I don't have to keep rubbing it to make it react. Once it reacts, it can keep going. Everybody, that makes sense to you?
Yeah.
This is very classic chemistry. This is all, everybody has this on their chemistry test. So here's our graph of it. And you have to know this graph. And what it is you've got energy on this side, energy on this side, time on this side. The catalyst is the next blank. Time on this side. You start off with the energy of your reactants. They're not reacting unless you give them this little hump of energy, and then they can continue on their own all the way to the products. So you'll have to label this reactants, products, activation energy is that little extra energy needed to get the reaction going. We definitely see that like with a log. Say you want a fire in your fireplace and you don't have gas to start it. It's hard to get those logs going. Even though the wood is there that's going to react, the oxygen is there in the air that's going to react, it takes that extra energy to get that fire going. But once you do, the fire will continue to burn on its own. Does that make sense? Okay, so the next one is one thing that can lower the activation energy is a catalyst. A catalyst is a matchmaker that helps get the chemicals together. What is it in your body? What's the catalyst? You learned about it in biology class. It's made out of proteins.
Amino acids.
Carbs.
Cell wall.
Starts with an E. Enzymes.
Oh.
Enzymes. I didn't hear it. Enzymes are made out of protein. They get things together in your body, and it doesn't. It's things that help a reaction happen, but it doesn't take place. It's a matchmaker. So in your body, you learned about lock and key. Catalyst, remember that, where the molecule will hold one chemical here, another one there. They react and then it lets it go. Do you remember learning that in your honors biology class? I'm sure Mr. Curtis taught it to you.
Yeah, Mr. Curtis.
He's very good. He's a good, thorough teacher. All right, now I want to add something. One last idea. And I'm not sure if I'm going to test on this chapter or if I'm going to come back when we do solutions, but I want to go ahead and introduce this idea to you, okay? You can just do it on the back, wherever there's some room. Oh, yeah. Oh, yes, y'all had the words I just said, but I redid it. My computer had a virus last year.
What was you doing?
That was the reports. I let kids turn in the reports. That's why y'all all did posters. Because people last year did PowerPoint and all that stuff, and somebody gave me a virus through it. Okay, so I'll tell you what goes in the blanks. Some reactions do not go to completion and can be reversed. When they stop going back and forth, the point is called equilibrium. So write that down, equilibrium.
Oh yeah, I remember this.
Equilibrium. This is like your cell phones. Your cell phones have a chemical in there that when it reacts, it produces electricity. When all the reactants are used up and now go to products, then your cell phone battery is dead.
Where do you rate this at?
You run, there's lights on the back. So you run the electricity through it backwards, it will restore your reactants, and the reaction can keep going again. So the next blank is equilibrium expression. It is a formula, it's a math problem where you can figure out how far a reaction goes to completion. Does it go all the way like my match where I can't get my products back, or does it go somewhere in the middle? The last one is equilibrium constant. It's the value you get from the math problem that tells you how far the reaction goes. And there are certain patterns in nature. You're going to see this when you get to physics. And there are so many physics problems that are so much alike that there is these, that there's just over and over again in nature, you see these patterns mathematically. And the odds of that, happening in an accident, pretty slim. Well, one of the patterns you see in nature is this math problem. We're going to continue doing problems, and there's a lot of them that go by this format. And that is the math problem that comes with our constant, the equilibrium constant. How far does the reaction go toward completion? How you do it is you look at your reaction in this format. What it means is A, Big B, Big C, and Big D are my four chemicals. Little a, little b, little c, little d are the coefficients come from balancing the equation. You put the concentrations, square brackets mean concentration. You put the concentration of the products in the numerator raised to the coefficient, to the power of the coefficient. your exponent comes from the balanced chemical equation, and then you put the reactants in the denominator. So it's products over reactants, their concentrations raised to the coefficient from the balanced chemical equation. These concentrations will be given to you. You just have to know where to put them and how to raise it to an exponent on your calculator. Remember what parentheses do? Parentheses mean add, subtract, multiply, or divide. Multiply. So we're going to take the concentration of C, raise it to the exponent, multiply that times the concentration of D raised to its exponent that comes from the coefficient. So here's an example problem. Here's my balanced chemical equation. Nitrogen plus hydrogen makes ammonia. I balance it. It is one that is reversible. It's got the arrows going both ways. I want to know how far it goes. I put the concentration of the product on top. I raise it to the power of the coefficient. I put the concentrations of the reactants on bottom, and I raise them to the power of the coefficient. And then I multiply. What do you think? That's pretty easy, isn't it? I think last time on the test I made it where people just had to, from this, they had to write that. I didn't actually make them have to solve it.
Oh, that's easy. That's the whole answer.
That's the whole answer. Unless I give you concentrations, then you put them in and put the numbers in.
No,
That's what made the test.
Yes. But I don't know if it's on this one or if I'm going to put it on the solutions test, which I think is Unit 8. I think we're going to do heat first, or maybe we're going to do solutions next.
Ms. Blackburn,
Yes.
why did you decide to teach kids?
I really like it. I've worked in labs, I've worked in medicine, and this is by far the most fun. And that they pay me for this is shocking and great.
How much did you pay?
Not enough. Y'all need to vote for your teachers to get paid more.
I'll be empty.
Wait, so how many units do we have to do?
We will at least touch on up to 11, but some of them will be mini units.
Yeah, most because I know you have set curriculum, but some of it isn't it tentative?
Yes. All right. Like, share, subscribe.